And yeah, okay, so welcome everyone to the last day of the APIC school. I am going to chairing the first few sessions of today. And for the first talk, we have the pleasure to have Óscar Chimborazo here to talk about climate science. And Óscar has done his undergraduate degree at the Escola Politécnica Nacional in physics. And then he did a PhD at the New York State University in atmospheric sciences. Óscar has also worked at several public and private institutes, including the National Meteorology and Hydrology Institute, INAMI, in Ecuador. And he has worked on climate models of Ecuador and also on how climate change is affecting the climate of Ecuador. And currently, he is a professor at Yachay University. And Óscar, if you are ready, feel free to start.
Okay, thank you very much, Helga. For this talk, I prepared some slides about the work I have been doing for the last years, and they are based on the projections of extreme events on South America, but I am focusing on the Ecuador case, okay? So, first of all, let me say something about the motivation for doing this study. So we know that climate change is affecting all the life on the Earth. So we need to know what is the cause, or I mean, we are aware of that the global mean estimates based on land and ocean data about the change in temperature or the anomalies of temperature are rising in the last decades or after the Industrial Revolution, and that's why, and that is because we have been using a lot of fossil fuels, and we are having mainly CO2 contributions, CO2 gas contribution to the atmosphere or another greenhouse gases. So they are affecting the temperature over land. And it is causing that the hydrological cycle or hydrologic cycle is changing because we are having more energy in the atmosphere. And this is causing a different behavior compared to we had before or previous to the pre-industrial or in the pre-industrial era. So the CO2 levels in the last year or in the last decades, for example, here we have the level of 1950, and this level was behind, or at least at most 300 parts per million. But now the current levels are above 400 parts per million, and that is contributing to this change in the temperature. And it is just talking about CO2. There are other gases, like for example methane and other that contribute. And this is just to show you that we are, as humans, and the institutions are trying to monitor what is happening with the CO2 over the atmosphere. And we know that this, for example, for this date, we have the temperature, I mean, the CO2 is, the concentration is above 415, or well, as we show there in the previous graph, the concentration is different from is higher from the pre-industrial era. So this is a problem that we are facing now, and we know that global warming is happening. We have a level rise. We have a reduction of the glaciers over our mountains, and it is causing some impacts on the natural life. Okay, so for example, here in our country, in Ecuador, in the coastal region, for example, this is a city called Machala that is located in El Oro. And we have, for example, this plot. Okay, so this is one example. I'm sorry, on February 2016, and we have this plot, and is something that perhaps we can say that one extreme event is happening, and it has happened in the past. So in the current understanding of science, we cannot attribute just one or two extreme events to global warming or to the change in the atmosphere behavior, because we have always had extreme events. What we can attribute is the frequency of these events, or these events. They are happening more frequently because of the change in the dynamics of the energy in the atmosphere, and that is happening because we have more temperature, more energy, and it's causing the change in temperature. So we are having, not only in Ecuador but in other countries as well, in other parts of the world, these events. For example, here another region is Guayaquil. In 2017, we have another example of what is happening here. That's just an example in this city, in this town. There are another parts for example, in Quito has happened, and also here I have another example in the Amazon region, in this town called Puyo. So this happened in November 2016. So there are the floods. They are affecting, as I said before, the life over Earth, over our communities, and this is causing a lot of economic losses, and we are trying to understand what is happening, trying to we're studying what is how the future is gonna be about climate change. Okay, so for example, in the 2020 year, we had a report that the floods and the extreme rain were threats, and they were more frequent. And we have, for example, in the 35 years, in the last 35 years, 44% of these floods and extreme strong rains represented 44%. And then they were followed by the forest fires by 26%, the landslides by 11%, the waves of in the ocean, the earthquakes, tsunamis, and droughts, etc. But as we said, as I said, or as this report said, the floods are something that is causing this here in Ecuador a lot of troubles. 50% of that and people that has disappeared was because of the floods. Okay, that is an information from the risk service of Ecuador, the National Risk Service of Ecuador in 2019. And it's happening this this is an information that we have now. So this is a motivation for me and for other people that we need to understand that it's problem, and we need to address in some way what is happening, or at least to know what is the future coming. The last report of IPCC, or the last reports, are telling us that this problem is gonna be worse in the future, but we need to be prepared. And one of the ways to be prepared is to perform or to conduct more studies about this. Okay. So in March 2022, we have another example, a more recent one here. So the floods caused by the rains affected more of 200 families in this town called Babahoyo. So with this, we can know that the extreme events are a problem, as I said before. Okay, so this is just an example. I want to emphasize this because just one extreme event is, we cannot attribute just one extreme event to the global warming, but the frequency of this. How many are happening now? How are happening in the last decades? How many more times? So this is increasing. So we have this information from the IPCC of 2018, what it's saying about the future. It's estimated that the human activities have caused the global warming of approximately 1 degree Celsius with respect to the pre-industrial levels. And there is an uncertainty from 0.8 degrees Celsius to 1.2 degrees Celsius. So it's very likely that the global warming is gonna reach the 1.5 degrees Celsius between 2030 and 2052 if we continue with the same with our activities in the same way, and this is with a high confidence level. So this is from the last IPCC report from the physical science, the summary for policymakers in climate change 2021. The contribution of working group 1 made this graph to show what happened with, for example, the cold temperature extreme over land. So in a 2-year event, in a 10-year event, or in a 50-year event, based on the future global warming levels. This is based on the future projections of the models that are having, for example, different pathways, the socio-economic shared pathways, that tells you that, for example, in some of the scenarios in the future, we will have 1.5 degrees Celsius or 2 degrees Celsius or 5.4 degrees Celsius above the normal or the pre-industrial level temperature degrees Celsius. So here, for example, between the years 1850 to 900, we have one frequency, once of the events. But for example, now in the present, we have 3 times more than this era, the pre-industrial era. Or let's say that era from 1850 to 900, okay? But now, for the future global warming levels, for these 3 scenarios, when we will have a future with 1.5 degrees Celsius or 2 degrees Celsius or 4 degrees Celsius, we will have, for example, 4 more times. In 2 degrees Celsius, we will have 1, 2, 3, 4, 5, 6 more times, or 5.6 times, as said in this part here. And that extreme event in a more warm world, we will have an occurrence of 9.4 times of this event that is happening in a 10-year event. Okay, so this is telling you that this is one happening more frequently according to the models that we are studying. Also, the 50-year event, an event that is happening every 50 years. So, for example, from this era, 1850 to 900, we have once occurrence, but in the present we have 1, 2, 3, 4, 5, or 4.8 times. And for the future global warming levels, we will have 8.6 times for 1 degree Celsius. For 2 degrees, we will have 13.9 times more. And for the future, the warmer future, the 4 degrees Celsius, we will have 39.2 times. Okay, and this is for the temperature extremes. Something similar we have for the precipitation over land. And for example, for this event, for the 10-year event, for the 1850 to the 900, we have a period, an event, a heavy precipitation event that happening once, for example, between 1850 to 900. And in the present, we can say that it's also happening 1.3 times. But in the future, when we will have an increase in the temperature of 1.5 degrees Celsius, we can say that this is going to happen more, a little bit more, 1.5 times. With 2 degrees Celsius, 1.7 times the same event. With 4 degrees, we will have 2.7 times. Okay, this is for this heavy precipitation overlap. And for other variables, like for example, the agricultural and ecological droughts in drying regions, for example, the same thing. We will have droughts more frequent. At present, we have, for example, droughts 1.7 times, but in the future we will have 2.0 times. With 2 degrees, 2.54 times. With 4 degrees Celsius, we will have 4.1 times. So we are seeing that the models are telling us what is happening in the future according to different pathways. Okay. So well, with this a motivation, because we know that the problem of the extreme events is something that we want to address. We need to know about our country or any other region over South America or any part of the world. But we are focused in our country. So, for example, here I'm showing how is the climate of Ecuador based on a classification by Köppen guideline. So this classification, as you see, is telling you that the climate of Ecuador is very, very complex because, excuse me, because of the Andes Cordillera, because on the Andes Mountain. So they are representing a block to the atmosphere, to the winds, and is causing different types of climate. So climate in Ecuador is complex, therefore, the definition of extreme events depends also in the region or over the region that you are standing. So it's not the same, for example, an extreme event over the coast or over the Amazon, because they are different climates. For example, it's very natural that a very heavy precipitation occurs in the Amazon, and the same amount of precipitation it can be considered an extreme event over, for example, one town in the mountains, for example, Ambato or any other that is drier. So, or in the coast, when we can see the parts that are desert or arid here. So all depends on where you are. So it's important to know the climate of the country. So in this study, I am just showing in this slide what were the methodology and the data that I use. There is a product called the Climate Forecast System Reanalysis, CFSR, that has the temperature, precipitation, and other variables from the surface, from the different products like satellites, ships, and many other information. It represents what we have like observations for temperature, precipitation, and other variables. The other data that I used was the Community Climate System Model, the CCSM4, that was used for the forcing of the regional model called WRF that I'm going to talk a little bit more later. And also I use the Climate Research Unit temperature and precipitation dataset. And also we use the station data from the National Weather Service, INAMI, from Ecuador to do some validation of the model. For this work, I use the version 3.7.1 from Word. We performed 44 sensitive experiments using CFSR compared to observation, to see how the model is representing the temperature and precipitation variables that are the, I'm saying the more, not the most important, but the more representative and the more used variables that we have. And we use the minimum average bias and correlation metrics to see this validation. And we chose the set of parameterizations that best represent the precipitation characteristics of Ecuador during a period of 59 days. So the domains to study Ecuador were these, and you know that this model is a downscaling method, and use, for example, this community Earth system model that has a very coarse resolution compared to a high resolution like the final result that I got. When we talk about the downscaling methods, we need to perform several steps. We need a parent domain and a nested domain. In this case, I am showing in this the parent domain of this simulation. So the this is the parent domain with a 50 kilometers grid resolution. V is a nested domain with 10 kilometers grid resolution, and C, the red square here, is showing the analysis domain, the one that I chose that doesn't have any kind of problem in the frontiers because of the simulation. So that was the analysis domain. This is just an example of how this works, or how the model is improved by choosing a nested domain. So for example, the 50 kilometers domain is showing the Cordillera, the Andes Mountains, but we cannot appreciate very well the pattern of the mountains. But we see here in the right side, we have the model with topography much better represented because of the resolution is, in this case, 10 kilometers. For a simulation of climate, 10 kilometers is high resolution, because the simulations for climate are very heavy, are very costly. We need a lot of resources, computational resources. So for the weather, for example, for a weather a type of simulation, now the resolutions are much higher. For example, there are simulations of 1 kilometer resolution, or 2 or 3 kilometer resolution. But that is for the weather type of simulation. For climate, we have this 10 kilometer resolution is a much more better. It's a higher resolution because of the computational resources. This is to show you one of the results of the performance of the simulation that we did. M0005 here is showing the code of the station that we use. I don't remember exactly what the station was, this one, but it's showing how the model is approaching to the real, to the observed. In black is the observed, I mean the real data, and in orange is what the model is telling us. So for the daily the daily temperature, we see that the model is for this station. This is just an example. There are many other stations that we made the comparison, but for this talk, I just showing you this comparison. So the model has this performance for daily above in the panel A. On the panel B, we have this for month. So we have a pretty good agreement with this. Okay, so this is for precipitation, and also we have there a good agreement between the models and the observation data. Okay. So the RP and RS that I show in these are just the correlation numbers. I wanted to show very quickly another phenomenon, or something that we were studying. This is the elevation-dependent warming effect that is happening over the country alongside the extreme events that we were studying. So the elevation-dependent warming is an effect that is telling you that while you are going up in the high or in the altitude, the warming is higher. So this was a little bit observed according to observation. This is a picture or a cartoon or a figure that is showing you observation results or observational results. And it's telling you that it looks like, for example, here, that when you are up, going up, the temperature, the change in temperature, the trend, the Kelvin per decade trend is apparently going up. So to study this, we use the output of the model. So here is an example of the changes in radiation at surface, telling us that this is a problem that is happening, or not a problem, I mean a phenomenon that is happening, because one of the ways to answer this phenomenon was to study the change in net radiation at surface. And also because of this is happening, we try to see what happened in the cloud water path. That is just the integral from the top to the surface to the top of the ice and cloud mixing ratio that is blocking the entrance of the radiation. This is just an example of the same explanations for this effect before I continue with extreme events study. So here I now telling you what we use to study the extreme events. The index or the indices defined by the expert team on climate change detection analysis, or EPCCDI. We calculated 14 of the 27 indices from this group that they defined. We didn't calculate all of them in Ecuador because there were indices that are not that they don't represent, or they are not significant for our country. But these were selected because they were more important in our country. For example, this index called PRCP tot is total precipitation, or the annual total wet day precipitation. Okay, so this is the definition is the annual total precipitation in wet days where just the precipitation is greater or equal than 1 millimeter. Okay, but here the extreme event is, for example, the very wet days. This is an index called R95P. So the annual total precipitation when these are this precipitation, RR means the precipitation is above the 95th percentile. So that is called, that's the definition for very wet days. And this is, as I said, depending on the region that you are. Okay, and the extremely wet days is the R99P. So we have the annual total precipitation when we have this. Okay, and in this table, I'm showing the other extremes. For example, the cold days, the cold nights, warm days, warm nights, the consecutive dry days, the warm spell duration index, or WSDI. So, for example, this one is the annual count of days with at least 6 consecutive days when the temperature is above the 9%, the maximum temperature. TX means the maximum temperature, and when this is above 90% with 6 consecutive days with this, we call this the warm spell duration index. Okay, so these were the indices that we were using. This is just the web page of the group, just you can check the ITCCDA climate change indices. This is just 5 of the or 4 of the indices, but they are listed in this website. You can check that there. Here I'm showing the information from the network of the Instituto Nacional de Meteorología y Hidrología INAMI of Ecuador. The information was collected to compute the ITCC indices for the period 1980 to 2010. These indices were compared with the indices obtained from a regional climate model, the WRF that I was talking about. Yeah. This was forced by a reanalysis data set that um, uh, uh, that we used to do the experiments. Okay, and to do the extreme events over the Ecuadorian domain. Okay, so these are the distribution of the stations that we use to make the validation and also to see what happened. Okay. So the naming data, the details, the information consists of daily precipitation, maximum and minimum temperatures. Before the computation of the ATCC indices, they were quality control and process. The quality control consisted in eliminating unrealistic values from the 3-time series of each station, selecting only stations that cover the same period, 1980 to 2010, with less than 25% of missing daily values, because there were a lot of stations, but there were many stations, not a lot, but many stations, but many of them also had a lot of gaps. So we reject the ones that have more than 25% of missing daily values. And because of the method needs that the time series were complete, we use a methodology to fill these gaps with some of the information from the series of the corresponding station using the daily climatology. So I try to I use this because at least I can use the same information to produce, for example, something that is corresponding to the same station. Okay. The indices computation, what we use. We said that there exist 27 core indices recommended by this group, the ATC-CDI, but we use just 14 of these stations. What we use an R package called Climedex PCIC from this author, Ronald 2018. There's a paper where he describes how they use. And the indices from CFSR, WRF, Sense, WRF Control, RCP 4.5, and RCP 8.5 that were other models, I'm sorry, over the whole study domain using another R package called the Climedex PCC.net NCDF, that is for the NetCDF type of files that we have for the outputs of WRF and the other other products. Okay, so the annual indices were computed because for daily indices were a lot of time and in the future I'm trying or I'm thinking to compute this, but for this study we just use the annual indices. Okay. Because in this talk we were saying that I was showing you some products using the R package and Python packages. Let me tell you that R packages were used to calculate these indices and Python were used to calculate or produce these plots that are showing you the results. Okay. So, and also we have the Spearman-Rad correlation coefficient between the SST indices and this is for one index, the one that we said before, the PRCP, the total precipitation from the CFSR WRF, that is one of the results of the model, and also the observations. And we try to see what happened between the SST index and the precipitation and this index from the ATC-CD, and to see if there is a correlation or something like that. Okay, and we have some other indices related to what's happening or that is affecting climate over Ecuador. There is the Niño 1+2 index, the Niño 3 index, Niño 3.4 index. There is another index based on the Niño that's called ONI, the Atlantic modular mode, and we are showing something that I can show here very clear, but for another examples we have that the statistical significant quantities were with p-values less than 0.05. Yeah. Okay. I think that we can see here the catched regions. Okay, where we have this agreement. Okay. So the projected changes in stream, the validation also was performed using the PDFs or the probability density function of in this figure. Here was the index as it is compared to the observation, what is saying to the model. And for example, we here for total precipitation in millimeters for this station, MM037, we have a good agreement for this one with correlation 0.86. Okay, but for example, for another index, for example, SD2, or II, we have this, and we can see that there is some agreement in the peaks, but there is a little of, or I mean, a bias here. Okay, so we are saying that we can see that in some cases is better, is well represented, in other cases is not that well represented, but is decent represented. Okay, so these are the projected changes in the stream, the validation as well, with the PDFs using another metrics to see what is happening with the model and what is happening with the observation. There is another example of the total precipitation, the extremely wet days, what is happening with the correlations with these effects of the ONI and the El Niño +1+2, El Niño 3, El Niño 3.4, etc. Same thing for the other extremes event indices. Okay, so for example, here we can see there is a change in the TNX. Okay, and we see that for the future there is a change for an increase to the temperature in both scenarios. I forgot to mention that I use the scenario 4.5 and 8.5 to do to see what happened, to see what will happen in the future. Same for the trend. This is the degree Celsius per year that is changing as well for RCP 4.5 and RCP 8.5. And we can see in this 0.06 is greater than 0.02. RCP 4.5 is a low, not very low emission scenario, but a little bit low emission scenario, but 8.5 that is in the right is a higher emission scenario. Okay, and this is for the changes for the precipitation, so the change in the extreme wet and extremely wet days and the wet days. And we can see that in some parts there will be more wet days or weather days, but in some parts it looks like that according to the scenario we will have less precipitation. Okay, it depends on the region, but it depends also on the different regions. I'm sorry. And this is for another indices as another example that we can show about this. Okay, finally I want to show you that currently the new models or the new set of CMF6 are using a different kind of, no, it's not that different, but it's more complete type of scenarios that are the shared scenarios, the socio-economic shared scenarios, the SSP1, 1.9, SSP1, SSP2, SSP3, and SSP5 refers to a different kind of how the socioeconomic scenarios in the future will be. So there are some assumptions that the groups have defined that are also that are related to the kind of emission scenario. 1.9, 2.6, 4.5, 7.0, and 8.5. It means how high will be the energy that is released to the atmosphere because of the use of the fossil fuels. Okay, so in the future, or what I am working right now is using these new models to try to understand better what's happening or in the future, or at least what we can explain. Because as I said before, one important thing for us is to understand this for the future. Okay. Some final comments is that the results of this study are for the period 2041-2017, and they are indicating that there will be an increase in the hot extremes or the temperature extremes that are higher, and also they are wet or humid over the most of the regions in Ecuador. There is also an spatial variability that is very important in this projection of extreme events. And we can say that is related to the hydrologic cycle. And I would like to also emphasize that the regional models, the RCMs, regional climate models of high resolution, such as QUARF, that are configured to study climate, there are very handy tools, very useful tools to simulate these atmospheric processes that that help us to detect, for example, the effects as ADW in a more consistent way, and also the projections of the climatic streams over different topographic regions that are very complex over Ecuador. And I also, as I said before, is very desirable for us as scientists and as a community to ask for that the governments try to give economic help to studies, to do ensembles of many more models that helps to reduce the uncertainty. For example, for the forecasting of early alerts for this. Okay, so that's all that I have for this talk. Thank you very much for listening to me, and I would have any questions that you have. Thank you very much.
Thank you, Oscar. We already have a question in the chat to start. The question is it really difficult to predict the weather here in Ecuador, more specifically in Quito, than in other parts of the world? And if this is the case, then why?
Well, yeah, that's a good question. Thank you very much. I would say that it depends where you are. In some parts of the world, is easier to predict the weather just because there are not complex terrain. That is the main thing, or complex patterns of the circulation of the atmosphere. For example, it's more easy where you don't have a mountain that is blocking the path of the winds, and there is no turbulence, and it's not producing any other chaotic behavior. Yeah. But here in Ecuador, we have, as I said at the beginning of the talk, we have the Andes, we have a lot of valleys, we have a lot of things that are making the weather and climate very complex. So for Ecuador, because we are a small country, it's very complex. But for example, if you go to another, perhaps a bigger country that has a region where there is a mild conditions that are not very complex, or no hydrologic process or winds are more stable, we can say that in those parts are more easily the prediction or the forecasting of the weather is more easy. Therefore, the climate prediction is also more easy. All depends on the region. Yeah. So in some parts it's more difficult than in other parts, but that is easily understandable or understood because we know that the patterns depends on how the weather, how the winds, the atmosphere circulates. So you have something that is blocking you, something else is gonna happen. If you have a high altitude, something else is gonna happen. So it depends on the region. Okay.
We also had another question that was asking how long does it take to run this climate model that you did, and what sort of computational resources do you need for it?
Okay. First of all, this one that I performed in the yes. Well, it was performed over a supercomputer called Yellowstone like 5 years ago. Okay. So it took me about for one at least 3 months, I guess, trying to see how it happens for one of the of the scenario. But I made some tricks to use this at the same time to perform the other one, the other scenario 8.5. So, but that now has changed because the supercomputers are more powerful, a little bit more. I think that would take a little bit less if I will run the same thing. But the other thing is that now we have more process that we understand more, and we have more information that we want to run, and also we would like to run a model with a higher resolution. And if we do that, the time in the computation is going to be even greater than that. Yeah. And also it depends on also the number of levels that you have. There's a lot of things that that tells you how will it take. For example, the other day I was doing or I mean these days I am doing another simulation, not for time, just for web. And for example, to run 84 hours, just 84 hours, it took me 6 hours to run 84 hours. That is 3 days. That could give you some, but it didn't have the same amount of complexity of I did for this climate study. For climate study, I needed much more levels, like 51 levels. For the other one in the vertical. For the other one, for this one that I am studying right now, or for the weather, I just use, for example, 34 levels. That would reduce the amount of time to calculate or perform the simulation. It depends always on what we are going to do. Okay, and the resolution, temporal and spatial resolution. Okay.
Yeah, that's quite a bit of time. It's very computationally intensive.
Yeah.
Okay. Thank you very much, Óscar, for joining us. And will you be available a bit later as well on the chat if there are more questions?
Of course.
Okay, so everyone, if you have more questions, then please let us know, and we will try to get answers for you.